video we're going to do a Kc calculation. So Kc is the equilibrium constant. It's calculated by dividing the concentration of products over the concentration of reactants. So the value of Kc is only dependent on temperature, and we usually do Kc calculations on reversible reactions given by this symbol here. So if we do an example, consider the following reaction. We have sulfur dioxide plus oxygen, and that's converted to sulfur trioxide and vice versa. Amounts of sulfur dioxide, oxygen and sulfur trioxide were added to a flask with volume 2.5 decimeters cubed. An equilibrium was reached at a specific temperature. At equilibrium, the flask contains 0.055 moles of sulfur dioxide and 0.0829 moles of sulfur trioxide. The value of Kc is 38.2. Deduce the units of Kc and determine the moles of oxygen in the equilibrium mixture. So first, what we're going to do is we're going to look at the Kc calculation. So Kc equals the concentration of products over the concentration of reactants. We know the units, the SI units of concentration, are moles per decimeter cubed. So to deduce the units, we just have to cancel out the units of the products and the reactants. So what we have is Kc equals, so in this reaction we have one product and two reactants. So we have the concentration of sulfur trioxide, but because the stoichiometric coefficient is 2, it's to the power of 2, so squared, divided by the concentration of oxygen, multiplied by the concentration of sulfur dioxide, and that has a 2 coefficient, so it's squared also. So we know the units of concentration are moles per decimeter cubed. The square brackets mean concentration. So here, when we just think of concentration, we can think of moles decimeter cubed squared divided by moles per decimeter cubed multiplied by moles per decimeter cubed squared, right? Because they all have the same units as in concentration. So when we cancel down the units, this divides by this, so we're left with moles per decimeter cubed, but that's on the bottom. So in another way it looks like this: 1 divided by moles per decimeter cubed. So when you divide a fraction like this way, the units of Kc are basically mole per mole decimeter cubed. So that they're the units of Kc. They're different to each equation depending on the number of reactants and products and also the stoichiometric coefficients of them. So it also says in the question to determine the moles of oxygen in the equilibrium mixture. So to calculate moles, we use the equation concentration equals moles over volume, and that's how we use to calculate the concentration of these. So to calculate the moles of oxygen in the equilibrium mixture, we need to figure out what we use to calculate Kc. So Kc, the equilibrium constant, is 38.2. Right, that was given in the question, 38.2. And that is equal to the concentration of products divided by the concentration of reactants. So products, reactants. So that is equal to, so our product was sulfur trioxide with a coefficient of 2, and we were told that at equilibrium the flask contains 0.0829 moles of sulfur trioxide. So this is 0.0289 divided by 2.6, which is our volume of the flask. 2.6. And we have a 2 here because there was a coefficient of 2 in front of the sulfur trioxide. So if we do the same for the reactants, we had oxygen. We were trying to determine the moles of oxygen. So question mark divided by 2.6 because they were all added to the same flask. The coefficient of oxygen is 1. And then for sulfur dioxide, the flask contained 0.055 moles of sulfur dioxide. So 0.055 divided by the volume, which is 2.6, and the coefficient of sulfur dioxide was 2 SO2. So that's squared also. So if we rearrange, because we've got a complete equation here, if we rearrange to find the moles of oxygen. So I would do 0.0289 divided by 2.6 squared, and I would divide by 38.2 and multiply by this. Basically swap their places. So 38.2. So now that we've got that, we're going to divide by this portion. I'm currently verbally speaking out my solution because if I turn the page then I'll forget all of this. So we have 38, we have this top portion divided by 38.2, and then we're going to divide this portion. So ANS divided by 0.055 divided by 2.6 squared. That gives us 7.2278 10 to the negative 3. Now once we've got that, we need to multiply by 2.6 to get the moles. So the moles of oxygen are 0.01879 moles of oxygen at equilibrium. So, I'm just going to go through it on the next page. I'm just going to go through my working out for this. But that's all the examples we're going to be doing today. So we have 38.2 equals 0.0289. Okay, so I'm just going to rewrite the question so you can see the working out. Because I think it's really beneficial to understand how we get that question mark. So I basically moved this lower portion up and this upper portion below. So if I rewrite it, we have question mark divided by 2.6, 0.055 divided by 2.6 equals 0.0289 divided by 2.6 squared divided by 38.2. So I've just swapped this lower portion up and this upper portion below. So I've done this calculation, which was 0.0289 divided by 2.6 squared over 38.2. So that gives me this number. I usually leave the answer in the calculator so we don't round too early. Then I divided by this portion here. So we had question mark divided by 2.6, and we're just going to divide by this. So we have and divided by 0.055 divided by 2.6, and that was also squared. So that gives us 7.227810 to the negative 3, and then we multiply by 2.6. And we've got 0.0188 moles of oxygen at equilibrium, which is I think what we got. Yep, which is what we got previously. So that's how you do KC calculations.